Welcome to all. So today we'll be continuing with the blast load and its effects on the structure. So in the previous lecture we saw about the unconfined blast. We looked into the free air blast, surface blast. Okay. So today we'll be switching over and we'll be looking into the confined blast. Okay. So confined blast or confined explosions. Okay. So we'll have a nice introduction to the confined explosion. Definition of a confined explosion. Okay. The explosions which are confined within the structural boundaries, okay, or which are enclosed or partially enclosed are termed as the confined explosion. Okay. So here we can see, let us say a blast occurs in this structure. Okay. So it is confined from the three side. So we put this thing into the partially confined structure. Okay. So if a blast occurs, then it is treated as a confined explosion. Okay. Similarly, in the load structure we can see the blast is occurring though the structure is confined on all the sides, but it has vents. Okay. It has certain vents on the top and it has certain vents on the lateral directions. Okay. So this is also termed as a confined blast, but with openings. Okay. So what happens during a confined blast? Okay. So the initial shock pressure inside the structure can be extremely high. Okay. Due to the confinement, there will be multiple reflections. Okay. The amplification of the pressure occurs due to the reflections within this confined space. Okay. So once a blast occurs, the incident wave is traveling and then again it is hit back with the boundaries. Okay. So there will be multiple amplification in the magnitude of the pressure. Okay. In addition to that, there will be accumulation of hot gases and the elevated temperature will be generated additional gas pressure. Okay. In this confined explosion, the blast pressure, the heat and all this energy has nowhere to go. Okay. So this will be keep on accumulating on the structure. Okay. So if we look into that, a confined explosion versus an unconfined explosion. So in an unconfined explosion, the blast has a way to has a path to travel out. Okay. The gases, okay, and the heat, everything has a way to dissipate. Okay. But in the confined explosion, it has nowhere to go. Okay. So that the effect in a confined blast will be severely larger. Okay. For the same charge weight, okay, let us say we are taking, let us say 1 kg of TNT. Okay. So the effect of the pressure wave in a confined blast wave is significantly more than an unconfined blast. Okay. So what is the takeaway from this thing? In case of an unconfined blast without proper structural design, okay, this large accumulation of the pressure will lead to the structural failure. Okay. Let us say for a surface blast or an air blast, and if we just apply it without taking into account the accumulation of the pressure and the effect of the gases and the other quantities, okay, there is bound to be a failure. Okay. Mitigations. Certain times the venting may provide the reduction in the pressure, but due to the operational nature, the venting may or may not be possible in all the cases. Okay. For example, if this thing is used as a data center or if this thing is used as a bunker, okay, so there the scope of providing venting minimizes. Okay. Let us say this is being designed for a CBRN structure, okay, a structure that has to resist the chemical, biological radiation and the nuclear threats. Okay. So we cannot have large vents out there. Okay. Then the design of this structure, okay, to resist the blast loading has to be done in a proper way. The accumulation of the pressure has to be accounted properly. Moving ahead. So types of confined structures and venting. Okay. So depending upon the venting and the confinement given, the structures are categorized into different categories. Okay. So first comes the vented structures. So the vented structures are cubical type of structures with one or more open or frangible surface allowing pressure to vent. Okay. So there can be multiple surfaces or there has to be at least one surface that allows the venting of the pressure. So for an example, a fully vented cubicle is where explosive gases escape rapidly and the internal gas pressure is often negligible. Okay. So this is a case of a fully vented cubicle, okay, where there is ample opportunity, okay, there are ample openings for the gases to escape out. Okay. Then there comes the partially confined. In a partially confined structure, it will have limited vent area. Okay. So, the amount of venting is limited. There is an buildup of the internal pressure and it leads to the substantial gas pressure acting for longer duration. Okay. So, in the first case there was proper venting, okay, where explosive gases were allowed to escape. Okay. In partially confined structure there is a limited venting. Okay. So, as a result of that, the buildup of the initial pressure is more and it leads to the buildup of the gas pressure. Shock pressures plus gas pressure both contribute to the loading. Okay. So, due to this accumulative nature, the actual amount of pressure experienced by this structure is large. Okay. Then comes the third category, that is the fully confined structure. Okay. In a fully confined structure, it is totally sealed and it leads to the large buildup of both shock and gas pressures. Okay. It especially, see, normally what we will say, we want a fully vented structure. Okay. But due to the operational nature, as I was saying, if it is a data center, okay, or if it is a vault of a bank, or if it is a bunker, especially a CBRN type of bunker, okay, there the scope of providing vent is almost negligible. Okay. So, then we come into the regime of a fully confined structure. Okay. So, due to the nature of the accumulation of the pressure, the shock pressure and the buildup of the gas pressure, this structure needs to be designed properly to account for this large accumulation of the pressure, even though the threat level can be from a minimal amount of charge, but due to the accumulation, the amount of design requirement becomes stringent. Okay. So, the fully confined structure has to be designed properly. So, this becomes a big challenge in the structural design. Shock pressure, what happens to the shock pressure in confined explosions? Okay. The shock pressure characteristics. Okay. So, it attains a very high peak pressure due to the internal reflections, as we said. Okay. If this is the incident pressure, okay, there will be a great augmentation in the reflected pressure. Okay. So, the reflected pressure will be significantly higher than the incident pressure. Okay. So, it occurs due to the internal reflection. Next thing what can happen is that the non-uniform distribution to the surface might occur. Okay. So, near to the explosion there will be high intensity of the loading, and on the other surface the distribution might be non-uniform. Okay. As we see that the distribution of the pressure depends upon the normal distance from the charge. Okay. So, even if you look into this wall and depending upon the placement of this charge, okay, the distribution, all the distances are different. Hence, there will be the distribution of the pressure will be different, and again on the other wall, depending upon the distance, okay, the distribution of the pressure might be different. Okay, in these two opposite walls. Okay. So, we will have to account for the worst possible case when we are designing for the confined explosion. Okay. This is in addition to the reflections that are occurring. Okay. Here we are talking about the distribution of the pressure. Okay. The spatial distribution of the pressure. Okay. So, calculation methodology, what we can do to account for this or to estimate the pressures. So, the peak and the impulse values are evaluated at multiple points and integrated to obtain the total load. Okay. So, as I was saying, okay, so even in this case of a box, okay, the pressure value will be different in all the walls depending upon the relative location of the explosions. So, what is being done is that peak pressure value and peak impulse value are calculated at different points, and they are integrated in totality to obtain the total load that is being acted upon the walls. Okay. So, for the design, average uniform pressure and impulses are used considering structural redistribution of the load stresses. Okay. So, we assume that once the structure is able to respond to the blast loading, okay, there will be a redistribution of the loads. Okay. So, to accounting for that, we design for the average uniform pressure and impulse. Okay. So, we design in an average sense. Okay. Otherwise, the design might prove to be highly uneconomical. Okay. If we assume the maximum intensity that is occurring at all the points. Okay. And since the structure, due to its redundancy, it can redistribute the load. So, we take into account this property. okay, and we design for the average uniform pressure. So the influence of the geometry, so the size, charge location and the internal surface configuration plays a critical load, okay. The size of the structure, okay, the location of the charge, okay, inside the structure and the internal surface configuration, okay. Two things comes out to be here, how these things are oriented in respect to the blast loading, okay, and how the internal surfaces, what they are made of, okay, what type of material they are made of. All these things plays a crucial role, okay. So in addition to the weight of the charge and the location of the charge, the entire configuration of the structure also plays a key role in determining the response of the structure to this blast loading, okay. So here we are showing the different barriers and cubical configurations and parameter, okay. So we can look at it into different types of structure, okay. So here if we are looking in a plan, okay, and we are looking into a cantilever wall, okay. So here we are looking into a 2-walled cubicle, this is a 2-walled cubicle, here we are looking into the plan, okay. Again 3-walled cubicle, okay, and a 4-wall cubicle, okay. After that here 2-wall cubicles with roof is given, 3-wall cubicle with roof is given and a 4-wall cubicle with roof is given, okay. So here this is just a cantilever wall, this is having 2 walls, okay, like this, okay. Here there are 3 walls, okay, like this, okay. 2-wall configuration, 3-wall configuration, here it is 4-wall configuration, okay. Here 2-wall with roof is also there, okay. This is a 2-wall configuration with roof, this is a 3-wall configuration with roof, okay. Here 3 walls are there and here a fully box type of cubicle is there, okay. So these are the different types of configurations of the cubicle can occur, okay. And depending upon this configuration, it may be considered as fully vented or fully confined, okay, depending upon how much we are allowing the pressure and the gases of the explosion to come out of the system, okay. So this case is the most critical one, okay, because this is the fully confined region, okay. So the effect of the gas pressures, okay, what is the nature of the gas pressure? So due to the accumulation of the explosions, okay, there is a excessive amount of heat produced, okay. So the gas pressures normally are lower in magnitude than shock loads, but they have a longer duration, okay. The shock load will dissipate faster, but they will have high magnitude. Gas pressure will have lower magnitude, but they will take longer to dissipate, okay. And the effect of the gas pressure is affected by the vent size, okay. Smaller vent areas yield longer duration and higher gas pressure, okay. This is obvious, okay. If the venting is small, okay, then the accumulation of the gas pressure will be more and it will remain for a longer time, okay. So timing, so the gas pressure rise lags behind shock pressure. So we know that shock pressure moves with a very high velocity and the gas pressure will move behind that with a very low velocity, okay. But for the design purposes we can take them together, okay, we can take both of their effect together, okay. There comes one term, this is called frangibility. What does it mean? Okay. So the frangible elements, okay, in a frangible elements what will happen is that it will instantly fall apart, okay. So they will be lightweight and there will be breakaway wall panels, okay. So what will happen is that when an event occurs, this will all break away very smoothly, okay. So this frangible elements are used to reduce shock amplification and enable faster venting, okay. So the elements with mass and resistance below defined thresholds, okay, are considered as fully frangible, okay. I will give you one example of a frangible elements, okay. In normal airports, okay, that have a smaller distance between the runway and the boundary wall, okay. So there are sentry guards, okay, there are sentry posts, okay, located on different locations, okay. So what is said is that if a aircraft comes and lands out here, and if it tries to veer into the two sides, okay, so that aircraft might be damaged from the after hitting this sentry post, okay. Mind here, we are not talking about the damage to the sentry post, we are talking to the damage of the aircraft, okay. So the sentry post is so designed that in the normal dead load, live load, earthquake, wind cases, it can resist all the loading, okay. But if it is hit by an aircraft, it will dismantle, okay, it will break away, okay, instantly, okay. So a normal threshold load is there, okay, as per the aircraft guidelines there is a normal threshold load. If this structure sees as an impact load, the whole thing will be dismantled, okay, it will, everything will fall apart, okay. So this is one more application of the frangible element. Same concept is used here also. So frangible element barrier, okay, is kept, and what it will do is that the main purpose of this thing will be to reduce the shock amplification, and it will break away, okay. So it will provide as a venting element, okay. So as I said, okay, due to the operational nature, okay, the structure might not have vents, okay. So here instead of vents, this frangible elements are put, okay. So for the normal operational conditions, dead load, live load, earthquake load, wind load, okay, they will behave as a single unit, okay. But when an explosion occurs, okay, this frangible element will fall apart, okay, and they will act as a venting measure, okay. So these are light away breakaway panel, okay. So they are used in the case of aircraft impact also, they are used in case of blast loading also, okay, and their aim is to reduce the shock amplification, okay. So this might be one of the threshold so that the structure may break away, and they are considered as fully frangible, okay. So this is one application of a frangible type of element. Moving ahead. So here we are seeing the reflection factor. So the reflection factor for the shock loading on frangible structure is shown out here, okay. So for a partially vented explosion, okay, the distribution of the pressure is shown, okay. So this is the scale range, that is from 0.2 to 100, okay. So depending upon the scale range, okay, so this is nothing but my Z factor, okay. So depending upon, for the different Z factors, this reflection factor has been considered, okay. Okay. So again, these are the curves for the different scaled gas impulse, okay, where volume fraction and impulse are considered, okay. So for the different cases, depending upon the scaled vent area, okay, the gas impulse is being shown, okay. So this is A by Vf, okay. So total vent area divided by the total volume, okay, okay. So here you can see, okay. So let us try to do one example, okay. So in this question, what is given, okay. So incident blast wave parameters, okay. So depending upon this configuration, we have to find the different blast parameters, okay. So this is my point of interest, okay, and this is the occurrence of my blast loading, okay. So the weight is 350 pounds, okay, and we have to calculate at this particular point, okay, 30 feet below and 40 feet away in air from air burst of here, okay. So we will try to solve this problem, okay. So first of all, we will look into this thing, okay. So we will have to decide what to consider, okay. So it has a finite depth from the ground, so we will call this as an, we will classify this as an air burst, okay. So we will try to solve this thing, okay. So first we will have to identify the TNT charge, okay. What is the TNT charge? Then we will have to determine the height of the burst, and then we will have to specify the point of interest, okay. So wherever we want to calculate it, and if some other metals are used other than TNT, then we will have to increase the charge weight by 20%, okay. Okay. So we increase by 20% to account for different types of charges. So, geometry, we calculate the distance, okay, and then we calculate the scale distance. Okay. So, using different curves, okay, from UFC 340, alternatively we can use TM5 1300 also. They are the similar curves. Okay. So, earlier what used to happen is that different arms of the defense services had their own different manuals. Okay. So, the army had TM5 1300 manual, Air Force has different manuals, Navy had different manuals, SEALs had different manuals. Okay. So, now what has happened is that all of them have been combined and a unified document is being used, that is the UFC 340. Okay. Earlier it was TM5 1300, so this has been superseded by UFC 340, but the graphs are similar. Okay. So, once we obtain the parameter, okay, once we have obtained the Z, okay, so from Z using any of the graphs we can obtain the peak positive incident pressure, shock front velocity, scale unit positive incident value, positive depth, arrival time, phase wavelength. Okay. Similarly, from figure 2.7 we will get the positive quantities, from figure 2.8 we will get the negative quantities. Okay. And after we have the negative quantities, we will multiply the scale value by weight to get the absolute parameters in terms of pound per square inches, millisecond and feet. Okay. So, this is the approach that we will follow for each of the example. Okay. So, first we will have to identify the TNT, determine the height of the burst. Okay. So, basically the point of interest, this is used to determine the type of charge. This is used to quantify what type of explosion is there, air burst, surface burst, okay, confined or whatever it is. Okay. From there we will multiply it by 1.2, that is the 20% increase to account for different types of charges. Then we will find the distance r, okay, from the explosion to the point of interest, what is the distance r, and then we will use the scale distance z. Okay. So, once we have z, we will use the UFC charts. Okay. So, in this particular one we can use TM5 1300 or UFC 340 charts, and using the appropriate figure for the appropriate type of blast considered, we can calculate all the different parameters. And once we have all these parameters, all these parameters are in terms of scale numbers. Okay. So, then we will have to multiply it by the cube root of weight to get the absolute value in the respective units. Okay. So, this is the normal procedure that we will follow. Okay. So, here we have to find we will move to the next example. So, in the next example we will have to find a free field blast wave parameters for the specified explosion scenario. Okay. So, this is the weight of the burst. Okay. So, it is being considered as air burst. So, this is the height of the burst. Okay. This is the height of the burst. This is the ground distance. Okay. This is the ground distance, and then we are asked to calculate the different parameters. Okay. So, we will follow the same procedure. First we will apply the safety factors. So, applying the safety factor. So, we were given 20800. So, we were given 20800. So, we multiplied by 1 times and we got the equivalent burst, okay, equivalent weight. Okay. After that we tried to calculate the scale geometry and angle. Okay. So, scale geometry we are getting the value of z, and the angle of incidence we are getting as 73.3 degree. Okay. Okay. So, using figure 2, 9 and 10 for air burst from again the same manual, we calculate the reflected pressure, we calculate the scaled impulse quantities. Okay. And after that we will multiply them with the cube root of weight to calculate these quantities in an absolute sense. Okay. Okay. So, again we calculate the quantity z, and then we are getting the other quantities. Okay. So, again using different figures, different appropriate figures, and getting the quantities z, okay, we are able to calculate the different quantities, shock wave velocity, scale time of arrivals. Again they are given in terms of scaled parameters W1 by 3. So, if we multiply by the weight quantities, we will get the absolute sense. Okay. So, again scaled impulse, see all these quantities are scaled. So, whatever we are getting from the graph, they will be the scaled quantity. So, we will have to multiply with the appropriate weight factor. Okay. So, this is how we can solve the problems. Okay. So, in all the problems, first we have to quantify type of charge, okay, either TNT directly or some other charge. Then depending upon this charge configuration, we have to multiply with 20%. If it is some other charge, we multiply with the 20%. If this is TNT, we ignore this factor. Okay. After that, depending upon the configuration, we determine what type of charge, what type of burst is it is, what type of explosion is this thing, air burst, free air burst, surface burst. Okay. And depending upon this quantification, okay, after that we also calculate the value of z. Okay. So, using these two parameters, the parameter of z and the appropriate figure, okay, from the UFC 340, okay, we get the corresponding graph from the surface burst, this burst, air burst. Okay. So, we get the corresponding graph and we read out the different values. Okay. And all these values will be in terms of the scaled parameters, and then we apply with the cubic root of charge, and then we will get the quantities in their actual units. Okay. So, this is the process that we will follow for all the examples. Okay. So, with this I end the lecture. Okay. So, what I will ask is that you please practice this type of problems. Okay. Problem number 1, okay, problem number 2, okay, and try to check your answers with the answers provided here. Okay. If there is any confusion and if there is any issues, you can contact us and then we can have a discussion on that. Okay. But again I am saying that, again I am emphasizing that please practice this type of problems. Okay. So, what these problems are trying to do is that we are trying to first assess the demand. Okay. We are first trying to assess the values of the pressure, okay, the applied pressure. So, all these quantities are demand quantities, okay, depend on the location of the blast and the point of interest, okay, type of blast, okay, okay, surface blast, air blast, free air blast. Okay. Depending upon the type of blast, the type of explosives used, TNT or some other explosives, okay, we are trying to calculate the demand quantities at a given point of interest. Okay. We are trying to calculate the incident pressure, the reflected pressure, the shock wave velocity, impulse, duration, positive duration, negative duration, okay, positive wavelength, negative wavelength. Okay. So, all the quantities of interest we are trying to calculate here, okay, so that the signature of the or the effect of the blast load at any given point we are able to assess and we are able to quantify it properly. Okay. So, we follow this methodology. Okay. So, given any scenario, you start with this procedure. Okay. First identify the type of TNT. Okay. So, depending upon what type of charge is there, we will have to scale it up to 20%. Okay. After that, determine the type of explosion occurring, surface burst, okay, free burst, okay, air burst or whatever it is. Okay. And after that, we will try to calculate the point of interest. Okay. The point of interest might be given. Okay. So, we will try to calculate the distance, okay, r. Okay. So, these three things are key. First, we will calculate these three parameters. Okay. Once we have these three parameters, we will calculate the z factor. Okay. So, once we have the z factor, then what we need to do is that we need to find out the proper curve depending upon the type of blast, okay, depending upon the nature of the blast, okay, we get the respective curve. Okay. So, here on the x axis z will be there and on the y axis different quantities will be there, okay, scaled quantities will be there. Okay. All these quantities will be scaled. Okay. So, using the appropriate curve depending upon the type of blast from UFC 340 or we can use TM 1300 also, this scale quantities will be calculated. Okay. So, once we have the scale quantities, then we will multiply them with the cubic root of weight and then we will get the actual quantities out here. Okay. So, this is the way we will try to use and solve for all of the problems. Okay. So, I end the lecture here. Hopefully, you will be able to do the exercises. Okay. And if there are any questions, anything, please get back to me. Thank you.